Before we begin talking about three-dimensional geometry, let's review some of the very basics about area in two-dimensional geometry. Do you remember the area formulas for these figures below? Well, obviously this first figure on the left is a square. And when we refer to the dimensions of a square, since they're all the same, we usually just put a little s here and say, well, that's the side of the square. And obviously, since it's a square, they're all the same. So the other dimension will also be s. This simplifies the area formula for a square as being the area being equal to, well, side times side, which will be your side squared. Now, as soon as we elongate one of the dimensions of a four-sided figure that has 90-degree angles, it clearly becomes a rectangle. So obviously we can't talk about all of the sides being the same because they're not. However, you could see that opposite sides are still the same. And you all know that we usually refer to the longer side as the length, L, and the shorter side as the width, W. And quite simply put, it's not that different than the area of a square where we're multiplying the two dimensions to find the area. So here the formula for the area of a rectangle is going to be length times width. And let's not forget that area, is really referring to how many squares cover up an entire two-dimensional figure. So area is usually spoken about in square units. But that's old school stuff, right? We all know that already. But let's talk about the perimeter now. Well, the square still has four equal sides. Let's still refer to them as S, the side of a square. But if we're referring to the perimeter of a square, we're not concerned about what's covering the figure. We're interested in knowing the length of the line that goes around the figure, as if we were going to construct a fence around this figure. So we're not multiplying anything, but what we're going to do is remember that these are all the same. All of the sides are the same. And we're just going to add up all of the sides. So in this case, for the perimeter of a square, we're really just saying S plus S plus S plus S, or to do it a bit quicker, we're just going to take S, the side, and multiply it by 4, giving the very simple formula for the perimeter of a square as being equal to 4 times your side, or 4s. Well, what about the rectangle? Well, the rectangle, as we said before, has a length and a width. However, the opposite sides are always going to be congruent of a rectangle. So that will also be the length, and this will also be the width. And now if we go around in a circle and start adding things up, we're going to get L plus W plus L plus W. Then we're going to add all the L's together, and we're going to add all the W's together, and we're going to get the formula for the perimeter of a rectangle is going to be 2 L's when we add L plus L, plus 2 W's, W plus W. And there's our formula for the perimeter of a rectangle. But this is all old school, and we are ready to get into three-dimensional geometry. Which brings us to this figure. What am I? Anyone know what that's called? I think I have it here somewhere. Oh, yes, it's a cube. Yes, it's a cube with a smiley face. Hello, Mr. Cube. Yes, a cube is the most basic three-dimensional unit. It is equivalent to what the square is in area. You might remember, regardless of what we were finding the area of, whether it was a square, a rectangle, a circle, or a triangle, we always measured area in square units, how many squares it would take to cover a two-dimensional figure. Well, three-dimensional world is no different in having its basic unit. And the basic unit that we're going to talk about is a cube. A cube. How many cubes we need to, say, fill something. Yeah, so the two questions that the cube calls out for is how much water is needed to fill me? But the cube also sometimes wonders how much paper is needed to wrap me? So this right here, everybody, is the equivalent to the two different areas that we're going to discuss in three-dimensional geometry. The same way in two-dimensional geometry, we're concerned about the area, but sometimes the perimeter. Well, in 3D geometry, we're sometimes concerned with how much space you need to fill something and how much paper is needed to wrap something. So does anyone know what these are called? What do you call how much space is inside a three-dimensional figure? How much water you need to fill this cube? What do you call that when you're trying to figure out how much paper is needed to wrap something up? Ah, so if you guessed volume and surface area, you are correct. Well, let's take a look at this basic unit first, the same way we start with a square in two-dimensional geometry. Let's start with our basic unit, the cube. Now, this is a cube because, like a square, all the dimensions are exactly the same. However, a cube has 3 dimensions, a square just has 2. And because it's a three-dimensional figure, I'm not going to actually refer to these as sides, even though sometimes they are referred to as sides. However, when two flat surfaces meet each other to create this right here, we call this an edge. So I'm going to, instead of putting an S here as I would for a square, I'm going to put a little E. And that little E here, I'll just put up here, put it up over here. Little E is going to represent the edge of my cube. Well, if this is a cube, it means all the dimensions are the same. So that means this dimension here and how far back it goes will also be E. And going up and down here will also be E, right? This is a three-dimensional figure. So it has 3 dimensions, E, E, and E. Well, to find the volume of a cube, I'm going to use capital V, is as simple as, well, remember we found the area of a square. It was a side times side, side squared. Well, here it's E times E times E. So since there's 3 here, we're multiplying E times E times E. It's not going to be E squared. It's going to be whatever the edge is to the 3rd power. Right? You know, whenever we have a little 2 up there as an exponent, we say it's something squared, right? It's like area. Well, when we have a little 3 here, you could say to E to the 3rd power, or you can say E cubed. Quite simple. All right. So that's the volume formula, right? E to the 3rd power. Well, how about surface area? Well, this is going to get a little bit more complicated, right? With surface area, we're not really concerned with what's inside, but how much paper you need to wrap something up, right? So the surface area is really figuring out the area of one of these faces, right? And what is that face? Well, that face is a square, and it's a square that has 2 dimensions that are exactly the same, right? This down here, the base right here is E, and the height up here is also E. So if I was trying to figure out the surface area, how much paper I needed to cover this, I often, when I talk about surface area, I take an S and an A together, and I kind of link them together, that SA, because I don't want you to think it's 2 different variables here. It's surface area, right? It's one thing. Well, the surface area of this cube will be equal to, well, first let's find the area of one of these squares. Well, we know that the side squared is for a square. Well, here we're talking about E. So E squared E times E, would give you the area of one of those faces. But we know that cubes, dice, blocks, right? We know that they have 6 different faces, and each face on a cube is exactly the same. So once you've calculated the area on one of these faces, all we need to do is multiply it by 6, getting the formula for the surface area of a cube as being 6 edge squared. So the volume is e to the third power, or e cubed, and the surface area will be 6e squared. All right, let's put this to the test here. All right, so you could pause your video right now and see if you can answer these 2 questions on the top. How many little cubes were necessary to construct this larger cube here on the left? And this is the same as the larger cubes. Go ahead, pause your screen and see if you can answer those 2 questions. Okay, so if you came up with 64 cubes, you were correct, right? And if you came up with this is the same as the larger cube's volume, you were also correct. Well, let's see how we could have done this formulaically. Well, if you knew that what you really were calculating here was this larger cube's volume, you would say, well, let me find out what one of these edges happens to be. Well, let's count. 1, 2, 3, 4. And because this is a cube, you could see the other dimension is also 4, and also that the other dimension, the third dimension, is also 4. Well, we happen to have just learned that the volume of a cube is really just the edge to the third power. Well, the edge here happens to be 4. So I'm going to work from left to right here, which makes the volume would be equal to, let's substitute 4 into the edge to the third power. Well, still working left to right here. Well, that would make the volume 4 to the third power, which is 4 times 4 times 4, which is 64. And when we talk about volume, we don't talk about square units, we talk about cubic units. And then you would have gotten your answer, or you could have just counted those all out if you had the time to do so. And yes, this is the volume, right? That's why we used the volume formula. All right, stage 2. How many squares would you need to cover this entire cube? This is the same as the cubes. See if you can fill in the number and the word for these 2 questions. Go ahead, you could pause your screen. Okay, well, here we have a different story. Here, we need to figure out not the volume, but the surface area. Right? We want to count all of these up right here, and how many of these are going to cover this, right? That's the same as the cube's surface area. And if you counted up all of the squares in one of those faces, you're going to get 16. Well, if you happen to know that that cube has 6 faces, you're going to multiply that together, and you're going to get 96 squares. So you got to be careful here. I know we're in the world of three-dimensional geometry now. However, volume, how much space is inside a figure, how much water you can put inside a figure, that's going to be three-dimensional units, cubic units. However, when you're just wrapping something up, you could just open that up and it's really just going to be paper. It's really just going to be two-dimensional. And therefore, we still talk about surface area in square units. Let's see how we might do this formulaically. Well, we just learned that the surface area of a cube is 6e squared. Well, the edge here is still 4. So we would have just plugged in our 4, right? And we would, you could just put that in the calculator. However, if you want to see what's happening, how we were able to just kind of figure out on our own here, we would get 6 times 4 squared, which is 16, which equals 96 square units. Great. Let's move on. Okay, so now we could get to slightly more advanced reasoning here. So here's, as we're warming up here now, let's see if we could figure out a problem that involves both volume and surface area in one problem. It says, if this cube has a volume of 1,000 cubic units, what is its surface area? Go ahead, pause your screen and see if you could work this one out. Okay, let's see what you accomplished. Well, here, systematically, if I read a problem and I'm looking for a couple important words here, I'm looking for, well, what's my figure? Cube. Okay. And what are we talking about? Well, they mention volume, but they also mention surface area. So in a problem such as this, I'm going to write out both of those formulas. I'm going to say, well, if we're talking about the volume of a cube, that's going to be equal to the edge to the third power. But if we're also talking about the surface area of a cube, that's going to be 6e squared. Well, here, there's two variables. I got my volume and my edge. I like to make a little table. And here, in this formula, there's only two variables as well, right? Cube is very basic. Surface area, remember that's one variable, and also my edge. Well, obviously, if I knew what my edge is, because it's the same cube here, I could figure out both of those. However, what's given to me in this problem is the volume. The volume is 1,000. So I'm going to have to use this formula here to reverse engineer to figure out what that edge has to be. Then I can just move it over there and figure out my surface area. So I'm going to substitute into the volume here, 1,000 is equal to my edge to the third power. Now, up until now, for most of your mathematical lives, you've gotten x's or variables that have been squared. And you, in order to undo a square, you used a square root. Well, guess what? There also exists something called a cubed root. Now, a cubed root kind of looks like this. It kind of starts out looking like a square root. But since a square root is the smallest one that we use this symbol for, we assume that there's a 2 sitting in this check mark. So that's why we never write it. So we want to do a cubed root. We draw a square root, but then we put a little 3 right in that check mark. That means the cubed root. And of course, if we're going to cube root one side, we got to go to the other side and also cube root. Now, a cube root. So to take a cubed root of a number in your calculator, there's a couple different ways you can go about it. Well, but first we're going to go into the math button. And if you look down at number 4, you're going to see a little 3 with a little square root and a little parentheses. That's usually the quickest, best way to get to the cubed root. Math, 4, and then you could see that a little 3 appears with a square root and says, okay, put in your number. So we're going to put in our number, which is 1,000. A lot of you might have been able to do this in your head. That's okay. And you get 10. Yes, that's right. 10 is the cubed root of 1,000 because 10 times 10 times 10 equals 1,000. So here, our edge is equal to 10. Well, then I can put my edge right here. We just figured out that this right here on this cube is equal to 10. Well, if the edge is 10, the edge is 10. So I could also bring it over here to the other side here and say, okay, we have an edge of 10. Now we can continue on to find the surface area by substituting 10 into my surface area formula. You got to remember the order of operations here. If you're doing this without a calculator, that you square a number before you multiply. So this is going to be 6 times 10 squared, which is 100. And the surface area of this cube will be equal to 600 square units. All right. We're going to wind this up by talking about a rectangular prism. Okay. We use the word prism to talk about three-dimensional solids where if you look at any particular face of it, right? A rectangular prism, like a cube, has 6 faces. If it maintains its size throughout the figure, that is a definition of a prism. So a rectangular prism is a unique type of prism because if you looked at any, like a box from any different perspective, and you looked at the rectangle here, say in the front here, this front rectangle, if you look at the back of that box, that rectangle is exactly the same size. So it's a prism in that direction. However, if you looked at the box from the side and looked, the width and the height here, you would notice that that also is exactly the same on the other side. And if you looked at the top rectangle and you went straight down to the bottom, you would notice that that is the same exact size, right? Everyone here knows what a box looks like. Well, a box is a rectangular prism. And in the world of volume, how much water, how much air, how much space is inside this box is pretty quite simple, right? You might remember that the area of a rectangle, a two-dimensional rectangular prism, is just length times width. Well, all we're doing is adding one dimension to that, say height. So volume, big V, of a rectangular prism is really as simple as just multiplying all the dimensions. Your length times your width, and add one more, times your height. Volume of a rectangular prism is length times width times height. That's probably the easy part of a rectangular prism. The surface area gets a little bit more complicated, right? How are we going to figure out how much, say, paper that we need to wrap up this item here, right? How are we going to figure out the surface area of a rectangular prism? Well, here you need to be a little bit more careful when you're talking about these faces here. Let's look at this front face right here. This front face is a rectangle, and we know that the area of a rectangle is, well, length times width. However, the two dimensions of this front rectangle, when it's a three-dimensional box, is length, and then if I go up right here, see my height here, this is also going to be my height. So the front face is going to be length times height. So I'm going to write down here, I'm going to start with that front one, length times height. However, we just talked a little bit about this being a prism, and there's only one other rectangle of the 6 rectangles that make up this box that's exactly the same as this one, the one all the way in the back on the other side. That's also going to be length times height. So there's 2 of them, so we just say, well, let's multiply that by 2. Well, we've now taken care of 2 of the 6 faces of that box if we were going to wrap it up with paper. So I'm going to have to add something to that. All right, let's talk about this one on the side right here. Well, yeah, length times width is the area of a rectangle, but the 2 dimensions are not length and width of this one. It's width and height. It's width, height. This one right here, the side rectangle. Well, that side rectangle, I'm going to write it down. Okay, width times height. But that also has another one on the other side of the box, which is exactly the same. So I'm going to multiply that one by 2. And now I've taken care of 4 of the 6 rectangles that encompass this box? Well, now we have to go to the top. And the top one is the famous one that we all love from two-dimensional geometry. It's length, right? This is my length, and this right here is my width. So this is my length times width. So I'm going to add a length times a width. And of course, the one on the top will be exactly the same as the one on the bottom. So there's two of those. So that is our formula for the surface area of a rectangular prism. 2 times L times H plus 2 times width times height plus 2 times length times width. All right. Now, as we go through this, they're going to be more and more solid. So one thing that you're going to want to do, especially when we get to our final test of the year, which is going to be on solid geometry, you're going to want to collect all of these formulas in a nice chart. So at home, you should, maybe create your own in your notebook, and you could always utilize it in all of the tests or quizzes that we have. So let's review what we've learned today. We learned that the volume of a cube is just the edge to the third power, and that the surface area of that very same cube will be 6 times one of the edges squared. And then we learned that the volume of a rectangular prism is as easy as multiplying the 3 dimensions, but the surface area gets a little tricky. Oops, I just see that I made a little mistake here. Oh, sorry about that. That's surface area. And that the surface area of a rectangular prism will be 2 times. Now, if you forget which combination, it really doesn't matter. You just have to have all 3 combinations. So let's start with the L and the H, 2 times L, H, plus, and then let's do WH next, 2 times WH, plus, and then the length and the width is the last one. If you mix those up, that's okay, as long as you realize that you have all 3 different possible combinations with your length and width. There only are 3 ways you could do that. And there you have it. Now, I think there was one more problem here that I just wanted to do. Yeah, there's one more hiding over here. So let's get rid of this one and see if we could do this last problem. And we'll call it a video. So here we go. The volume of the prism is 720 cubic units. If the length is 24 and the width is 6, can you find the height? Okay, let's see if we could handle this. So again, volume is what we're talking about, and I could see in the picture that this prism is a rectangular prism, right? That has length, it has width, and it has height. And I know that the formula for the volume of a rectangular prism is length times width times height. So on the side of my paper, I'm going to take all of those dimensions and make a little table and see what's given to me. Well, they're handing me the volume, and they're giving me the length. And they're also giving me the width. And it's the height that they're asking us to find. So I'm just going to leave that as h, and I'm going to substitute all of these numbers into my formula. My length, which is 24, my width, which is 6, and leave the h because that's what we're looking for. So this becomes just straightforward algebra here. Well, 720 will be equal to, well, let's simplify this, 24 times 6. Well, that's going to be 6 times 4, which is 24, carry the 2, 12 is going to be 144 h. Okay, well, there, now we got to solve for h. I'm going to divide this by 144. I'm going to divide this by 144. That cancels out, and my h is going to be equal to 5. Right? The height would be equal to 5. Find the height. My height is equal to 5. And let's leave that there. Well, I hope you found this video useful. Volume, surface area, part 1. And if you did, please subscribe to Mr. Frank's YouTube channel.